Hi, I'm Robert, and this is GraphqlD doing the boring things. GraphqL is a query language for the web, basically a REST successor. GraphqlD is a server implementation for this GraphqL standard. Basically, you can think of it as a bad SQL implementation returning JSON. So the interesting bits about doing a GraphqL server implementation. One of the interesting bits definitely is the parsing. GraphqL itself is an LL1 language, meaning that a recursive descent parser is very easy to write. But that is not actually fun or interesting. So instead you can create a parser generator that creates AST classes for you and also creates the parsing in it. And as it's LL1, it's very easy to do, and you will get basically recursive descent parser with custom classes for each of the production of the grammar. That's quite fun. Also very interesting is the validation of your query. So GraphqL defines a type schema, and with that you have the capabilities of doing basically type checking on your query. So one thing that you can check is that you pass in known types. So for instance here, the first argument to this update user mutation is a string. And if the string weren't defined, you could say, hey, type error, can't process this query. What is also very fun to check is that all variables are defined. So looking at this mutation again, and the mutation is basically the post in REST speak, we see that we have a mutation called update user, which takes one parameter called name, which is of type string. And the exclamation mark behind the string basically tells you that this string must not be null. And then inside of this update user mutation, we have a call to update user, which is the actual function that we want to call on the backend. And here we see that we have an assignment of user ID with the $sign in front to ID, and an assignment of name with the $sign in front to name without. And here we see that user ID isn't actually defined. So we could tell that we will throw an exception that the variables or arguments aren't all defined, and we can't process your mutation here. And there are quite a few other validations that we can run. Basically, what it all comes down to is AST traversal, looking at the schema and seeing if the requests match the type definition of what our backend is exposing. All quite interesting work. Also very fun is turning these structs into GraphqL structs. So on the left, we see the struct query, and on the right, we see the type query type. And type is basically GraphqL speak for struct or class. And looking at the first member of our struct called ship selection, we see your basic D function. You have a return type called starship, and you actually return an array of that. And you have input of IDs, which is a long ID. So presumably this function gets you all the starships listed by the IDs in the parameter. On the other side, in the GraphqL implementation, we have the same name, but then the return type is written on the furthest right. So that's the starship in square brackets with 2 exclamation mark. And as said before, the exclamation mark basically states that the thing must not be null. So the return of ship selection in this case is a non-null array. So we always return an array even if it's empty and not null, as you could do in JavaScript quite easily. And also all the starships inside will not be null. So each element in that array will be a starship or it will not be in. For the parameters, it's basically the same. It's called IDs as it's called in the destruct, but then again, the type goes after the column. And here again, we say we want all longs or ints in this case, as there's only one integer type and it's basically long, but they call it int, and it must not be null, none of the entries. And turning those destructs into the TypeScript schema, onto the TypeScript type, is interesting work. It's involving a lot of AST or traits, walking all the members, making sure that the conversions work, that you turn your longs and your ints and your bytes into the right type. And the same goes for the string and the default parameters and so on and so forth. But all these bits are already done. So now we can actually get some work done and use this thing to build useful interfaces people can get useful work done with. And these I call the boring bits. Boring in the sense that we're not doing any of the fun bits as listed before, but still this might be interesting for you if you actually want to build a GraphqL server with D. what is actually entailed in resolving a request. So taking this request here, we would like to get all the starships that are over a size of 120 meters. And for all of those, we would like to get their ID and their designation. Basically, you can think of this as a JSON without the values. So if you glance over the oversize parameter to starship, you basically have the keys of what kind of JSON you're expecting. You want an array of starships, and each of these objects, or now starships, in your return JSON array should contain two members, the ID, which is presumably a number, and the designation, which is going to be a string. But how to actually get about it? Before we go into how to resolve that, we have to look at what kind of setup we have to do to actually get starting. So one thing that will come up later quite often is the custom context, and this can be any struct you define that will be passed to all the resolvers that actually later will turn the requests into JSON and return that. But here for now, for simplicity's sake, we just have one member, the user ID, and we're going to see that used later as well. Then there are some options we can define for the GraphqlD backend, but we're going to skip those. You can look those up in the documentation. And then finally, we create our GraphQL instance. This is sort of the thing that takes the request and gives you JSON back. And that has two template parameters. One is the schema and one is our custom context. The custom context we already discussed, but the schema is basically a struct containing at least one member, which is the query type we saw earlier. And then there's the mutation type, which is basically the post part of REST here. And this schema is basically the named entry point in what kind of data we can query. And GraphqlD is going to take that and introspect all those members of the schema, and from there introspect all the return types and all the parameter types and so on and so forth. Then we need something to parse, and here I abbreviated the query string from earlier with the 3 dots, get the string from somewhere and put it into to parse. And then additionally there is a JSON object called vars for variables, which should, after you got your request, contain all the variables associated with the query you want to parse. Then you create a lexer and a parser. We basically take the lexer, pass it to the parser, and then you parse the document. And this document and clean new instance of your custom context, you pass to the execute method of the GraphqlD instance we created earlier, in addition to the variables. And then somehow in the end, you get JSON object called result, and that is what you ship then back to whoever did the request. So as said before, we need to resolve this, and this is done by resolvers. And this here is how you define and set a resolver. So the resolver has to be linked to a member of a type, and the type we want to link this starship resolver to is the query type, and the name of the member we want to resolve by this delegate we pass in here is the starship's member. And this delegate has to take 4 arguments: the name, the parent. These 2 we're going to ignore for now, but we're going to come back to them later. And then we have the args, which is short for argument, and a reference to your custom context. And this custom context is always passed in via ref, so you can actually change whatever is stored in there for housekeeping tasks and stuff we see later. Now what this delegate does, it iterates the database, and the database coming from somewhere else. We don't really have to care about that because very likely people have different databases, and we iterate those ships in the database, and every ship that is over the given size, and you can see on line 7 how we get the size out of the oversize argument, out of the arguments we passed into this starship's resolver. We're going to turn that into JSON and append it to a member called data in our return object. And every data that is returned has to be accessible by the data member of the return JSON from this delegate. So for instance, if we want to get a starship by ID and we would only get one starship or nothing, we would either assign the JSON resulting from turning this one starship into JSON to the data, or we would put in a null value to indicate that we didn't find it. And so finally, we have our JSON object and return it. And that's basically how you write resolvers. The interesting bit here is how do you actually take something and turn it into JSON that GraphqlD understands. We sort of turned this into the starship to JSON function, but obviously you would at some point write a D or a serialization library that does all this sort of boilerplate for you. But the interesting bits is here that again, we return JSON where the data member has been assigned other information. And the first thing that stands out is that there's an underscore type name string in this JSON, and this is called starship. So the problem that GraphQL faces is that it is only working on JSON, but it's still implementing a type system, and you have to have type information to do stuff with the JSON you see. And so the underscore type name is basically GraphQL's implementation of type ID that we know from D. The other 4 assignments here are then quite boring, so to speak, as we just set the names from the Starship members inside of the JSON we want to see. So for instance, here we set the ID to ID, the designation to designation, and so on and so forth. But maybe you remember that we actually only want to get the ID and designation. And here's sort of the first problem, the real problem we have to face. Either we could implement one resolver for every member of every type. So we would create our own resolver for ID. We would then also have to create another resolver for designation. But obviously that would lead you to write many resolvers. Probably some could be factored out and reused, but still that would be a lot of writing. As good programmers, we try to not write that much. So what do we do? By default, there is a default resolver in GraphqlD, which is called the default resolver. And this resolver uses the 2 parameters to the delegate we sort of glanced over in the beginning, the name and the parent. So the parent is the JSON that was constructed one level up in the nesting of the query. The default resolver for each of the entries in Starship is gonna get sent the whole Starship we constructed here. So type name, ID, designation, name, and size, all the members of Starship. And what the default resolver does, it looks if the parent has a member by the name of name. And if that is the case, it takes that member from parent and assigns it to the current object and returns it. And thereby we are doing a tiny bit of overconstruction in the JSON in the sort of quote unquote parent resolver. But that way we can get the default resolver to do quite a bit of work for us in the end. If that is not the case, so if there is no property or member in parent that is called name or the value stored in name, we have to construct an error because then the user tried to query for a value that was not in the type. And we do that by a member called errors. And errors is a member of the returned JSON that is an array. And each of those array elements can have 2 members, message and path. And path we're going to ignore because by default it's probably going to be the call stack of where the error happened in the query. But here the message is basically just saying no field by name found in type. And here we can again see how we use the type name to get the type of the thing we're looking for. And the get with default is basically a small helper function inside of GraphqlD that allows you to look into a JSON object without getting an out of bounds error if the element doesn't exist that is specified as a parameter. Instead, what you will get is the init value of the type you passed in. So in our case, if type name wouldn't exist in parent, we would get the empty string there. Just a tiny bit of convenience to make life easier. By this way, the default resolver will allow you to write far fewer resolvers than you would normally have to do. From here, we can do other stuff. Just sort of as a little bit of convenience, we're going to create ourselves an alias called resolver type, which is of the signature of the delegate taking the name, the parent, the arguments, and the context. And we're going to create ourselves a function called register resolver, where we pass in the GraphqlD instance and then the type, the name, and the resolver itself. And why this is handy, we will see in a bit. One thing that came up quite early when using this in production was that we had to keep track of how long different resolvers took, because eventually you likely will call a database to get information out. And if you have complicated queries happening very often, that will take long. And at some point, performance is playing a role here. So we have to benchmark, and benchmarking GraphQL sometimes is difficult as the user can provide queries and the user will provide you queries that you didn't expect. So if you didn't benchmark for them, you will have bad performance. So what do? You benchmark or keep track of how long stuff takes in production. And what this function does here is before we register resolver, we use the Prometheus package available on code.dlang to create an histogram thing. And that is basically just like a list of buckets where we store how long stuff takes and how often that duration appears in the runtime of the program. After that, we set a resolver, and this resolver is not the one we passed in the parameter resolver, but is a resolver that in the beginning starts a stopwatch, calls the resolver with all the parameters, so it's basically just a path through. And after that resolver is finished, it stops the time and stores that in the histogram we created earlier. So what this allows us to do is very easily take note of how long our resolvers take. Now, by having the virtue of this function, we can already we can do this for all the resolvers we ever want to register, and it just works without us having to think again. And the usage for that one then is basically this, right? The GraphqlD instance has moved as being the instance on where we call set resolver to becoming another parameter in the register resolver function. And the implementation of how we get all the starships over this certain size has not changed at all. It's just the same. Unfortunately, though, authentication here is not handled. And if you're staff lead, you maybe don't want to allow everybody to query your GraphQL endpoint and get the names and IDs of all the ships over a certain size. That's not how you do it. So we have to do some authentication. For that, we do another take on how to do stuff to a resolver or do additional work before or after a resolver. And here we have the check auth function that actually returns a resolver type. So it actually creates a delegate and returns it. It also takes a parameter of a resolver type, which it then at some point will call. So the implementation here is quite simple. And for user authentication, we sort of fake it a little bit by saying if the user ID is 0, you're not authenticated and can't call this endpoint. And here the test is basically, if that is true, we create a new JSON object and assign one error that says you're not authenticated and return it, and we're done. If you pass this check, so you have a user ID that is unequal to 0, we call the resolver that we passed in and pass it all the arguments we pass into this resolver. And we then just return it and we're good. A tiny bit of refactoring before we do it this way, just to show another thing that now can be done. So for instance, if the database were to be passed in by the custom context, we could make this get starships function, which is basically just a copy of the body of the delegates we saw earlier. And we could mock our database access for unit testing, for example. But then unfortunately, there's a tiny bit of housekeeping we have to do to make this function callable. So again, we call register resolver. But now what we do instead is we call check auth and pass to it the result of toDelegate, which again sort of takes the address of the get starships. toDelegates is just a function defined in Phobos that allows you to pretty much turn anything into a delegate. And here we take like a plain old function, get the address, turn that to a delegate, and pass that to check auth for all the types match. And now we have a function that not only checks that the user that is calling it is authenticated, but also takes time of how long the resolution of get starships actually takes. You can see how you can stack those forwarder functions to do whatever you have to do all the housekeeping, to do all the authentication, to do all the logging you ever want to do to your GraphQL endpoints. So far, we haven't really seen why GraphQL is called GraphQL. On the left there, we have a query where we again get all the starships, get their names, but then also we get their commanders. And as we can see on the right, the commander is going to be like a character of type character. And that person then also has a name and also has a ship where he or she is or it is a commander of. Obviously, the thing on the right wouldn't compile because D or any statically typed programming language can't figure out the size of those structs because character is a struct which is a member of Starship. So we have to know the size of character to calculate the size of Starship. But on the other hand, also Starship is a member of characters. And we also need to know the size of Starship in order to calculate the size of struct. So we have a cycle and we can't have that here. One thing that you could do is make those into functions. And then we could still introspect the members of Starship and get the commander and also get the ship in character. Those wouldn't have size in the struct itself, but there still would be the name. Unfortunately, if you do that and then also use the starship in character in other introspection work that is maybe not written by you or by GraphqlD, or you actually use those to do computation on them, it's quite easy to get an undefined reference to whatever you shouldn't be calling here. So I guess if you're on Linux and have used D, that error down there is something that you will likely have encountered before. And that is definitely something we want to avoid. So the way to do that in GraphqlD is there's a new type called nullable store. A nullable store actually doesn't have any members. The only thing it has is an alias to the template parameter or the template type we pass in. It still has the name, but GraphqlD knows how to get the actual type of commander and ship here. So the actual type will be character and starship in the schema that is created for GraphQL by GraphqlD out of the destructs. And you could now see how you can build out an arbitrary graph in your application. All you do is just link the different nodes of your graph via those edges here, via nullable stores. Another problem that will likely come up at some point is that you will have very, very long or deep queries. The problem with those is that at some point there's going to be repetition. For most of us, if you're not right now Facebook, at some point you're basically going from vertex A via some edge to vertex B and then via some edge back to vertex A. So and this case is a good example. Here we are basically just getting the crew of a ship many times over, and at some point you will have seen all the ships with all the crews and all the ships they are on. Here again, the custom context comes into play. And the custom context here is an awesome place to cache the JSON that you have already created. You will not have any cache invalidation problems, as for every request you get your own instance of your custom context. So no two queries, even though possibly executed at the same time, will share a custom context. So caching here is also then very easy. All you do is check in your custom context before you do the actual hard work of resolving your query if that information is already stored. And if that's the case, you just return it. And maybe a costly call to the database can be avoided that way. So a short commercial break here. Most of this work has been done by me while working at Symmetry Investment. I had a little bit of sort of testing done before, but the bulk of the work has been done while working for Symmetry Investment, and I still do. And we are looking for motivated people. So if you think you're motivated and are looking for new opportunities, please feel free to contact us. If you think boring work is actually very interesting, we have a lot of interesting work, and then probably also a lot of work where some people think, oh, doing those resolvers might not be that interesting, but most of the time they actually are. So feel free to contact us. Going back to the topic, GraphQL also has primitive types, and those types are basically all the types that are not objects or JSON objects. By default, the spec defines 4 or 5, depending on how you count. So there are ints, which are basically all integers, from byte to U long. Then there are floats, which are basically doubles. They are booleans, and they are actually booleans because JSON knows booleans, and then there are strings. And additionally, the spec defines an ID primitive type, but that serializes to a string. And I suspect as GraphQL was developed by Facebook, there's probably some legacy code that was requiring a special type there, or special type name. But we can ignore that for now because they're strings, so who cares? But what is really interesting is that even though JavaScript has a date object or a date primitive or library type, JSON does not, but GraphQL is, the reference implementation is in JavaScript. So even that is the case, there's no implementation of a primitive type of date. And there's also not a specification on how to get dates in object form to the user. So what you could quite simply do is have a new type of date that contains an int for the year, an int for the month, an int for the day, an int for the hour, and so on and so forth. But that is also not the case. So we have to do something here. Basically, what we have to do is to create custom primitive types. In GraphqlD, that is quite easy. All primitive types as defined in the GraphQL spec have to convert to a string. So here we have a GraphqlD custom leaf, as they're called here. We will pass in the type of what we want. And that's basically there to have a way of naming them correctly. Then you have two additional parameters, which is the D to string here and the string to datetime. And as the implementations below show, there are two functions. One takes a datetime and returns a string by calling to isox string. And the other one takes a string and calling from isox string creates a datetime again. Obviously, the string to datetime is not the complete implementation here, because if the string currently isn't isoxed datetime string, from isox string will throw, and you probably want to do some checking before that your deserialization here works correctly. But anyway, it had to fit on the slide, so that's the stuff you have to do, right? So we're already coming to the end. That is basically all you need to know to get started with GraphqlD. There's a somewhat okay example with good documentation in the GraphqlD repo that you can use as a starting point to get your Vibe application GraphqlD backend. Concluding, it can be said again that one more layer of indirection is basically the solution to all the problems. D plus GraphqL is a good fit, especially with the introspection we have in D. Creating much of the boilerplate for GraphqL was quite easy. It's basically after you have written one function to iterate the members of a struct, you have won the game. And also, it's not a toy anymore. This is actually used in production for symmetry investment for one of our internal projects. And the API is already quite big. We have many different types with many members, and the graph is very deep, and the queries we write actually are, I would say, maybe even too large, but that is sort of another problem for another day. But there's a lot of data that is wrangled there. So it's not a toy anymore. You can actually use this. And if you find any problems with that, please feel free on the GitHub page for GraphqlD to create an issue. And I will try to get to it as quickly as I can. But even better, if you have an issue, also create a pull request to fix that issue. And then I'm happy to merge that in. Obviously, if it fixes the problem correctly, it doesn't break anything else. But CI is up as well. So please take a look. And thank you for your patience and attention. Bye.